கூகுள் மீட் எப்ப பண்ணுவீங்க? வாங்க, அதையும் சொல்லிருங்க. கேசவன் சார், லிங்க் அனுப்பிச்சிட்டேன், அப்படியே பார்த்துருங்க ஒர்க் ஆகுதுன்னு. இது கூகுள் மீட் எப்போ ஓப்பன் பண்ணுவீங்க?
லேப்டாப் கொண்டு வர சொல்லியிருக்கேன்.
சரி,
ஆன் பண்ணிடுவேன்.
அது நீங்கள் தான் பண்ண முடியும்.
இல்லை, என் ஐடியில் தான் சொல்லுவேன்.
சரி சரி, அதையும் பார்த்துட்டீங்கன்னா லைவ்ல தான் இருக்குது, அப்படியே வச்சுட்டேன். இது ரெக்கார்டிங் வேணும்னா ஸ்டார்ட் ரெக்கார்டிங் ஸ்டார்ட் ரெக்கார்டிங் லோக்கல் டிஸ்கஸ் சிஸ்டம் இங்கே எங்கேருந்து எடுத்து வந்து உங்களுதா?
நம்மளுதான், எங்களுக்கு.
சரி,
எத்தனை மணிக்கு முடிப்பீங்க? முடிக்கிறது வந்து ஒரு 2 மணி நேரம் ஸ்டார்ட் ஆகிடுச்சுன்னா ஒரு 1.5 மணி நேரம்.
முடிக்கிறதுக்கு ஒரு 5
சரி, ஓகே, நான் கொடுக்குறேன். எல்லாம் எல்லாம் கொடுத்துருக்கு. நான் கூப்பிட்றேன். நான் ஃபோன் அனுப்பிச்சு விட்டேன்.
இப்போ நீங்கள் லைவ் போயிட்டு தான் இருக்குது, என்ன பண்ணீங்கன்னா தெரியும்.
தெரியும்.
ஏன்னா நான் பாஸ் பண்ணலாம், பாஸ் பண்ணிட்டு மறுபடியும் போட்டா ஸ்ட்ரீட் கீ போட்டா வேற மீட்டிங் போட்டுக்கலாம்.
The time of starting the game, அது போட்டு
டைம் போட்டுருங்க, எத்தனை மணிக்கு ஆரம்பிக்கணும்? சேலரி லிங்க் ஆப்பரேட்டிங் ஃபங்க்ஷன் ஸ்டார்ட்னு போட்டுருங்க. போட்டு பழகிடுமா? ஆமா, ஆடியோ கேட்டு பேசுறது.
இதுவா அது வேணும்ல இப்போதைக்கு மீட் பண்ணிடுங்க.
A warm welcome to all of us here. Sharing is a way of life that brings joy to everyone involved. To share the insights of recent advances in materials and manufacturing and so much more on the 6th International Conference of 2024. On behalf of Mechanical Department of Vedanta College of Engineering and Technology, I once again offer our most grateful welcome. I invite all the honorees to light the auspicious lamp of courage and wisdom.
Thank you all. The brightest star guide the way. When it was the brightest star in our sky, Dr. Subramanian sir, head of the mechanical department and chief coordinator, to attend this convention.
Good morning, everyone. So it's a great pleasure to have the 6th International Conference on Recent Advances in Materials and Manufacturing, edition 2024 at Delaware College of Engineering and Technology. Of course, this is the 6th series of conference. At ECET, we are conducting this 4th. So for this great event, first I wholeheartedly welcome our trustee, Sir Yamamoto Yoraja sir, for the inaugural function. Welcome you, sir. Next, I would like to welcome Dr. Kangar Prakash, Executive Director, Religion Tech Solutions, Coimbatore. We are in association with the company for the past 6 years, from 2020, from the COVID period onwards, we are conducting this conference. So they have a very great support for us in organizing this conference, as well as bringing the purpose in the scope of the journal. That is also most important. So thank you very much and welcome you, sir. So I would like to welcome Mr. Chandrasekhar sir, Secretary and Correspondent in Armenia, who is busy with this today. He will join us shortly. As well, I would like to welcome Dr. N. Jayaraman, Principal Visiting, who is not able to attend this function due to his personal reasons. I would like to welcome Dr. S. Velmani, Professor Mechanical, and Dr. R. Prakash, Associate Professor and Assistant Head Department of Mechanical Engineering, who is the coordinator of this conference. I would like to welcome the heads of other departments, in particular faculty administrator, Chief Chief Librarians, and all the faculty members and the non-teaching staff members of VCEP. Last but not the least, I would like to welcome all the participants hailing from various institutions throughout India for this great event. Once again, I cordially welcome you all for this great event. Thank you very much.
Thank you so much, sir. Greatness flourishes under the gaze of wisdom. I'm delighted to introduce Mr. Thammaprakash sir, the Executive Director of Originating Solutions, a visionary leader in the tech domain, who will now enlighten us about the conference.
Respected trustee of the level institutions, yourself. Respected the conference chair, the head of mechanical engineering, and the coordinators of Icramm 2024, and faculty members, and the keynote speaker, Dr. Sunil Rajan, so he is waiting to offer his keynote to online, and participants from various institutions joined offline and online. A very good morning to all of you. This ICRAMM conference series started in the year 2019. We started this conference at KLE Technological University, Welcome, in 2019. In fact, the first edition of this conference was ACT sponsored conference. And again, we thought of continuing with the same ACT sponsorship. But as you know, the next year was taken by COVID, and everything, even the format of the conference, the way, the execution of the conference, everything got changed once that COVID started to spread. And even in spite of that COVID, so we were fortunate enough to hold this series confidently, and we continued the series without any gap. So that's, I would like to thank Welland College of Engineering and Technology, particularly Principal Sir, Dr. Jayaraman Sir, who was my staff when I was doing my undergraduate, and Kumaravan Sir, for taking this conference here and making it possible even during the COVID. So we conducted the second edition of this conference in 2020 in a full online mode at Welland College of Engineering. It was a really nice experience. We had actually the first three conferences we had publication with FCS materials proceedings, and we continued with this. And 2021 we had moved this due to some commitment over here with other events. So we moved this to Divai Patil Kolhapur. And from then onwards, we have been continuing this conference at Welland College of Engineering and Technology, and it will be going on in this way. So every year, this conference in December, so we plan to conduct at Welland College of Engineering. And last year we had a publication with AIT and some other materials, science forum and engineering materials. And this time also we are planning to go with the AIT, and also this means that we will look for some other, because AIT takes a long time. Actually, they take at least 1 year, 1.5 years to publish a proceeding. But meantime, we will look for some other possible very good publication that AIT case. So we may push those papers to some other peer reviews also. But Scopus indexing is sufficient. So this time also we received a very good response from around the world. There are several countries, 5-6 countries we have received papers from, and participants are waiting to present their papers today. And we received more than 250 papers for this conference, and out of which around 85 plus papers are going to be presented today. Since we have less than 100 number of papers, we conduct this conference within 1 day. That is why we changed it to 31st, the second day of the conference. And today we have all the presentations of these 85 papers, and these 85 papers are very good quality papers. And all these papers, except papers which are registered for present or remote, all these papers will be processed for AEP conference proceedings, and subsequently they will be possibly indexed in Scopus. So once again, I would like to thank all the participants for having confidence and faith on ICRAM 2024, and this is the motivation that we have that actually makes the event to be happening every year. And with all your support, I would like to thank you all for attending this conference or participating in this conference. And once again, I would like to thank Kalala College of Engineering for giving continuous support and opportunity to organize such a wonderful conference here. Thank you all.
Thank you so much for your words, sir. To mark the proud moment of knowledge and collaboration, I'm pleased to invite Mr. Kandaprabha sir to appreciate Mr. M. Yoradha sir and trustee by providing the memento. I request Kandaprabha sir to extend his gratitude to our HOD Dr. R. Manavedra sir. And once again, I humbly request the token to be provided to the conference coordinator, Dr. R. Prakash sir. I request the memento to be given.
Thank you all. I humbly ask Mr. P. Deepak of the Mechanical Engineering to release the remarkable chief guest of the day. I make the floor.
Good morning to everyone. It's my great honor to introduce our esteemed chief guest, Dr. Sunil Jaising Roy sir, a leading expert in mechanical engineering who has joined us from Mutual Media. Dr. Roy is professor and head of mechanical engineering department at D.Y. Patel College of Engineering and Technology, Kolhapur. He completed his PhD in mechanical engineering from Shivaji University and has spent over 20 years contributing to engineering education. He has received international recognition for his research, including the Young Researcher Award by ISTE New Delhi in 2019. His work covers areas like robotics, automation, rapid prototyping, and advanced manufacturing. Dr. Roy holds 3 patents, including one for an automatic place sculpting printer, showcasing his idea string theory into practice. As a coordinator of AICTE Idea Lab, he mentors young engineers to think creatively and innovatively. He has published 55 research papers in respected international and national journals, collaborating with experts from Italy. His contributions to CIRP conference, a global leader in production engineering, highlights his influence worldwide. Apart from academics, Dr. Roy has worked in industries, gaining hands-on experience in quality control and advanced measurement systems. He also reviews research for top publishers like Elsevier, Springer, and SGAE. As a lifelong learner, he has participated in and lead many workshops and training programs on renewable energy, learning manufacturing, and advanced metrology. He has served as the Dean of Research and Development and played key roles in institutional improvements like anatomy and quality control. Above all, Dr. Roy is known for his humility, dedication, and passion for guiding young minds. Let us give a warm welcome to Dr. Sunil Jaising Roy sir, an inspiring engineer, educator, and innovator. We are delighted to have you here with us today, sir. Thank you.
Thank you, people. Now I request all the dignitaries to take the respective seats of the podium. Yes, sorry. Thank you. Yeah. Is it visible? Yes, sir. Can you start? Am I audible? Good morning, everyone. And Dr. Sunil Jaising, Head of Mechanical Engineering Department at DY College of Engineering and Technology, Kolkata, Maharashtra. At the outset, I mention my deepest gratitude to the organizing committee of this sixth international conference on recent advances in materials and manufacturing, organized by Department of Mechanical Engineering, Velara College of Engineering and Technology. The keynote address will be given on the future of polymer-based additive manufacturing, in which I am covering the material innovations and slicing techniques. Basically, this is the theme of presentation, in which I will cover some of the basic aspects of additive manufacturing, some future aspects of additive manufacturing. Since our topic is on material and slicing, I will cover most of these things related to polymer-based additive manufacturing, which we call 3D printing also. Some important aspects of materials, of course, again polymer-based materials and advanced slicing techniques. Because nowadays we are using a lot of slicing techniques. People are using because 3D printing is almost a technology which is since last 8-10 years. But people are not doing the advanced slicing techniques because with the conventional slicing techniques, so many things can be sorted out. But with advanced techniques, we can have a reduction in build time. We can improve the productivity of 3D printing. So that I will cover most of the times. Might be everyone is knowing now that what is meant by additive manufacturing. Since we add some material, it is known as additive manufacturing. And in additive manufacturing, we produce the components layer by layer by using the layers of material. That's why sometimes it is also known as layer by layer manufacturing, or sometimes it is also known as 3D printing. The basic advantage that additive manufacturing offers as compared to subtractive manufacturing, because before start of era of this additive manufacturing, everywhere there were techniques of subtractive manufacturing, which we call as the metal machining process. Casting was there. Casting sometimes is also referred because we produce material by pouring the molten metal. But when we compare these two basic techniques, additive and subtractive, the basic thing is their flows is exactly opposite to each other. In most of the subtractive manufacturing processes, we start with the bulk material, we reduce that bulk material, and we create the objects. Now, in this process, lot of wastages are there. For example, if you consider a simple turning process in which we reduce the material, bulk material to a cylindrical shape, for example, say, lot of chips will be there. So that will form a sort of a wastage. But in case of additive manufacturing, we start with very less material, which we can call as additive material, and we create a 3D model of component which is to be manufactured. And based on that model, we produce the final prototype or final component, we can say. As compared to subtractive manufacturing process, additive manufacturing produces very less and sometimes it produces very negligible wastage. That's why this technology nowadays is preferred by many manufacturing organizations. In fact, it is at the transformation stage because if we consider this additive manufacturing process, some limitations are there. If we overcome those limitations, you will see after 20 years everywhere only additive manufacturing process. That is what the potential this process do have. It falls in basic seven categories additive manufacturing, which basically have a process known as material jetting, in which we create objects a similar method to a two-dimensional inkjet printer. The process is somewhat similar to inkjet printer. Everyone knows the function of inkjet printer. So metal jetting basically works very similar to inkjet printing. In wet polymerization, we use a vat of liquid photopolymer resin. By using that, we basically produce the components. Yeah, yeah. No, I have not explained it. Is it at the same stage at the start? Because no. If it's not visible, I have changed three, four, five slides. It is changing now. So full screen it is not changing. So I will continue the same. Shall I continue the same? Yeah. I will continue this one. So sorry for the issue. I will just go back and I will show what I have covered. I will not describe this once again. But this is what I mentioned about additive manufacturing, in which I just discussed that in additive manufacturing we add material and we create the geometry. And when we compare subtractive and additive, the basic difference is that subtractive starts with bulk to produce the component, additive starts with very small material to produce the 3D object. So the difference of wastages is there. In case of additive manufacturing, very less, very negligible wastages are there. So these were the processes I was discussing. In material jetting, it is somewhat similar to our inkjet printer. Wet polymerization, we produce the objects by using liquid photopolymer resin. Binder jetting, it is somewhat similar to again material jetting. Material extrusion is one of the processes which is used almost everywhere for polymer process, in which we can have a process like fuse deposition molding, in which we actually fuse the material and we produce the components. Likewise, many processes are there. Our focus is not on the process because everyone might be knowing what the process is, what and how their principle works. You can go to lot of materials available for just know how material of things of additive manufacturing. We should focus ourselves as a researcher on the future of additive manufacturing. As I mentioned earlier, it has a huge scope in the future because right now it is at the transformation phase because we have some of the limitations with respect to material, and the major limitation of additive manufacturing is its time taken by this process to produce the prototypes because it's a very lengthy procedure. But as I mentioned, it is at the transformation stage. One survey was carried out in US, of course, in the medical areas, the use of additive manufacturing in last 3 years before 2023. So 2020, 21 and 22, in which some questions are asked and they come up with some surprising data of use of this additive manufacturing process. In up to 22, the prototyping with the additive manufacturing means simple prototype. It is not for industrial use. It's up to 66%. And still, of course, the surveys for the medical field, the anatomical models, they will produce some 47%, tooling patterns 31%, prosthetics 29%, surgical plannings 35%, and patient management user requirements it's like 26%. So surprisingly, at this stage, in 2020, there were people who mentioned, one person is mentioned, I do not use additive manufacturing. It was 15%. And in 2021, it increased to 23%, but from 2022, it has decreased. Nowadays, even small kids are knowing what is mean by 3D printing, what is mean by additive manufacturing. So that is how it has increased its uses from a very small, negligible use to the higher use. If you consider this data, the market size of additive manufacturing process, it is mentioned in billion US dollars. In 2023, it is somewhat near to 18 billion dollars US dollars, and it will increase. These are predictions, of course. It will increase to almost 110 US billion dollars up to 2033. So it has a huge scope. It has huge application areas. Our focus is on the materials of polymer-based additive manufacturing and the slicing techniques. So in polymer-based additive manufacturing, again, variety of processes are there. You can go through the simple aspects of this process. Fused deposition molding is there, in which we produce the polymer-based component using small filaments, wire filaments. In stereolithography, we produce the polymer by using resins. And some other processes are there, like digital light processing is there, SLS, which is called as a selective laser sintering, is there, polyjet printing process is there, sheet lamination, which is famously known as which is also there. But mostly FDM is a preferred process in polymer-based processes. Our focus will be surely on the material of these polymer-based additive manufacturing processes. But let us go through one very interesting slide in which you can see how much 3D printing has developed now. Because still many people believe that we are in the era of 3D printing, but I want to tell everyone that we are not in the era of 3D printing. Of course, we are in the era of 4D printing nowadays. Because in case of 3D printing, if you just consider before 87, there was an era of only molding, means the plastic molding processes were there, polymer molding processes. So after that, means with the invent of X-ray printing, my status is after 87, 1987, of course, it has increased a lot. The use of 3D printing increased a lot. And mid of like 2015, the invent of 4D printing is also there. It adds one more dimension to the 3D printing, which will be with respect to the time. So you can create some objects with 3D printing, and after some time, or according to the application, according to the situation, it will change their shapes, which is how we call as a 3D printing. Now the volumetric 3D printing is also has been invented. Lot of research is going on in the 3D printing in terms of material, in terms of their applications. Nowadays, the sustainable solutions are also coming out of the material, and so many things are there. The major challenges, because we are supposed to define the problem of today's presentation, because the presentation mainly will focus on the material and the slicing. The basic challenges, what I have raised are four basic challenges. One is the material limitations, because polymer, even in the metal also, material limitations are there. The limitations basically are with respect to their chemical properties, their mechanical properties, and their printability also, how we are printing them. Process inefficiencies are also there because a lot of heat is there in case of FDM printing, for example, polymer based. So working will be there, layer additions will be there. Many issues are there with respect to processes also. Two more aspects of challenges in the additive manufacturing is the very limited scalability is there for industrial applications. Because industries, again, they are not still preparing the components produced by the additive manufacturing. Some industries are preparing, but they are very high rate additive manufacturing processes. And the machines, equipment required for those additive manufacturing processes are very costly. So limited scalability is there and cost considerations because if we go for invention of material, advanced material, we require advanced equipment also. So cost aspects are there. But to resolve these main aspects which I have mentioned in the red color, which we are calling as material limitation and processing inefficiencies, they can be sorted out by using two basic aspects. One is material. Material is backbone of each and every 3D printing process. Because unless and until we get a printable material, we cannot use the 3D printing. So it is backbone of performance and innovation of all those things. And slicing is a very important aspect to improve the accuracy, to improve the efficiency, and of course to improve the customization in the 3D printing. That's why I have considered these two aspects for the presentation. So if we start with the basic things of the polymer-based additive manufacturing, in which we have material like polylactic acid, PLA, we call ABS, PET is there, nylon is there, PPU, which is in form of flexible material, polycarbonate, which is a very hard material. So basic aspects, they are defined with respect to their printability. Printability of almost all these materials, this basic material I am talking about, is a very, we can say a good printability, not very good and not a low printability, but it will be of a good printability. And if we consider their elongation and the breadth, so most of the material, the known material, the common used material, they have very less spread. So the basic aspect related to the virgin material or what we can say the basic material which are used like PLA, ABF, they have very less strength. That's why for superior applications like in medical devices, like in automobile, these are not suitable. So to go one step ahead, we have to make them in form of composites. So on the right side of this area, these are some of the composites. Composites, the famous composites is the glass fiber, the carbon fiber. These are the composites which are commonly used. But nowadays the companies, if you consider the middle section of this, which is in green, these are the companies which are manufacturing these composites. Like 3D Tech is there. ESA is a very group, very good group which who is manufacturing all these composites. So the composites like PLA carbon fiber, ABS carbon fiber, PLA glass fiber pitch, glass fiber iron, glass fiber ABS, glass fiber nylon. They have a huge scope to use a suitable material in automotive application because most of the application for these polymers, of course, this matrix is in the automobile. If I go one step ahead of this, these are some of the trends which are required to be addressed. Everyone knows the common choices like PLA, ABS, PETG, etc. Composites are also there, but nowadays the focus is on the sustainability, like recycling the material, recycling the existing material, new discoveries in the biodegradable polymers, etc. With the advent of these materials, we have the new word which we call as functional polymers. Now, functional polymers, for example, if we can have a conductive material, for example, if I mix PLA with the copper, it have some sort of conductivity. So that we can call as a functional material. In functional material, again, so many aspects are there. If we consider application-wise, we have application in machine engineering, drug delivery, energy, textile, food, water. You mention any area, there will be application of this 3D printing and the polymers. So polymers which are functionalized with biological nanomaterials, they are basically used for drug materials. Polymers which are functionalized with bioactive molecules, they are used for energy. Which are functionalized with bioactive molecules, they can be used in textile also. The active polymers can be used in food packaging. As far as conductive polymers are concerned, these are some of the applications. They can be used in batteries, solar cells, catalysis, capacitor, fuel cells. So many applications are there. If anyone want to do the research in this particular area, like in functional material, in composites, huge scope is there. Nowadays, people are doing, in our lab, we are doing a lot of research in the composites, basically graphene PLA composites, glass fiber PLA composites, carbon fiber PLA composites. Even we have tried with the metal composites also, like metal and the polymers. So we have tried with bronze, we have tried with copper, copper powder and PLA, etc. Very good and very fantastic results are there. They retain their mechanical strength. We have tested all the components for their mechanical and even some chemical aspects also. So they are giving fantastic results. So in new research is there who is looking in the for doing the research in the 3D printing. Lot of scope, huge scope is there in fact in the composites. To move ahead, a very important aspect of 3D printing is the slicing because the effectiveness, the performance of each and every aspect of 3D printing, mostly related to APM and SLA, is dependent on the slicing. So everyone might be knowing what is mean by slicing. Just left side of this, a small example is there in which I have shown the aspect of slicing. As the generic name suggests, slicing is to slice. That's all. So a 3D model of component is there which is to be produced with the 3D printing. So what we need to do is we need to convert it into the layers. And for this purpose, slicer is used. So slicer basically is a software module. Like Ultimaker, you write there. You have to differentiate yourself in these two aspects. The STL file will be generated with the CAD model. So software like Icramm, Katia, SolidWorks are there. You can create, you can generate the 3D model of that, and you can create the slicing of this in the slicer. Like Ultimaker, you guys one of the slicer. With respect to different printers, different slicers are there. So you can use those slicers to create the slicing of that, and after slicing, the 3D printing is done. So the data flow in 3D printing will look somewhat like this. You need to do the CAD modeling of the component. Even those who are starting newly in the 3D printing, you have so many resources, so many models are available on the different websites which are free to download. Initially, you can start with downloading those components. What you need to do is you need to download that and you need to convert it to the STL file. And after that, you need to slice it. You need to generate a G code, and that G code can be given to the printer. So a very simple and very self-explanatory process is there which we can use for this slicing. But if you go into detail, there are two aspects of the slicing. One is what you look at the front end and what is happening at the back end. A front end, you will find the graphical user interface, you will find the SQL visualization, and you will find the G code. But at the back end, so many things are being done. Like the slicer need to read each and every aspect of that model. It has to generate a slicing algorithm. It has to prepare a G code. If you look at a simple example, for example, suppose I am 3D printing a sphere. So what the slicer will do is, slicer basically use a SQL file. So that file, the file name came into existence by the name of process system, which is known as scale lithography. Sometimes SQL is also called as standard triangle language, or sometimes it is also known as standard tessellation. Now this word tessellation means we need to break a complicated geometry into the simple parts. For example, here, if you look at the sphere, sphere 2 is a somewhat simple geometry, but in slicer, what it will do is the spheres will be broken into different aspects, like which are just these aspects are just available above the sphere, like some triangles are there. So a simple sphere is broken into the simple, again simple parts in form of triangles. That's why the name is given as a tessellation. So breaking the complex geometry into the simple geometrical terms, you can say. So here again you need to follow some rules like vertex to vertex rule is there, orientation rule is there, all positive occurrent rule is there. So many rules are there, but these basic three rules are being used by most of the scientists. In case of slicing, it has a basic feature in terms of its parameters. For example, when you start 3D printing, For every process, there are some input parameters, there are some output parameters. Input we call as a process parameter, output we call as a response variable. So in 3D printing, we have basic parameters like layer height. Since 3D printing produces the component layer by layer, the thickness of that layer is known as a layer height. So we can have very small layers, medium layers, very high layers, etc. The shell, the outer boundary of that particular component, we might have single shell, double shell, triple shell, even you can increase the number of these shells. Inside the 3D print, we have infill patterns and infill percentage. So infill percentage basically indicates how much solid part you want from that particular 3D print. For example, if I put 80% infill, it indicates that 80% solid will be there, 20% part will be hollow. But that will not be hollow at a single aspect, that will be hollow at the thorough component and thorough material of that particular 3D print. For example, here different infill patterns are mentioned, concentric, hexagon, grid, so many patterns are there. With algebraic Cura, you will get almost 15 patterns. And one more important aspect is the orientation, how you are printing that part. So here inside the specimen is there. It can be printed in a flat orientation, it can be printed in vertical orientation, it can be printed in long vertical orientation. So 0 degree, 60 degree, 90 degree, 180 degree, these are some of the orientations which are available in the slicing. And two more important aspects are print speed. So how faster you are printing. So 100%, 80%, 90% print speed is there. Again in print speed, some movements are there where the nozzle will not print anything, it will just go from home position to the bed and then it will start printing. So you can define these things with respect to the slicer, with respect to the printer itself, and the temperature of printing. Now, again, in temperature, two temperatures will be there. One is known as extrusion temperature, other is known as the bed temperature. So, extrusion temperature matters a lot as far as the printing of polymer is concerned. So, these are some of the valid range of the printing temperatures and the bed temperature. In advanced slicing features, so many aspects are there. We cannot cover all those aspects in a presentation of 15 minutes. But what we can have is we can have an overview of these aspects. For example, in printing, because when we are printing polymers, the heated polymers rather, there is a possibility that during printing they will get adhered to the bed. There will be print failures, there will be warping, there will be issues with the aesthetic, there will be issues with the print surface, there will be issues with the layers. So many aspects are there. For that, one common advanced pricing feature is available, which is known as the bed adhesion. So we can have a few options in this. One is known as skirt, pre, and wrap. In skirt, if we just look at these objects on the right side, which are visible here, red is the object to be printed, and along that, in the blue colors, these are the slicing features. Now the first one is known as a skirt. In skirt, what the nozzle will do, it will print a small single layer around that object, and then it will start printing the actual object. So what will happen because of this is it will get adhered to the bed correctly and then the object will start printing. In brain, one complete layer will get printed, not one layer, but one complete layer of the actual printing will be printed first and then the component will start. And in RAM, a series of layers are printed. For example, in brain, one complete layer, in skirt, one line will be printed, and in RAM, 3-4 layers are printed and then component will start. So by using bed adhesion, you can prevent the print failures, you can improve the quality of finished part, you can improve the issues related to warping, etc. So you can use this advanced slicing feature to improve the quality of 3D printing. One more advanced slicing feature we can use is a support overhang. So support overhang basically is mentioned in terms of angle. It refers to the overhang angle threshold at which the support material will begin to be generated. Now in 3D printing, as you know, we cannot print the geometry as it is. We need some supports. Wherever some overhangs are there, some projections are there, what the slicer will do is it will generate the support. So that angle at which it will start printing the support is known as the support overhang angle. Here, I have shown the aspect with two overhead angles. One is with the 30 degree and one is with the 60 degree. Now, what it will do is, depending on the part geometry, if you provide a small overhead angle, it will cause more support material, and if we provide the larger angle, it will use very small material for the support, because material matters a lot. It is not only about the material, it is about the printing time also. So if we use a very small support material, the printing will be faster. If you use more support, the printing will be, it will take some time. So with the 60 degree and with the 30 degree, the savings in support will be, it will reduce almost 20% of time which is taken by the support. So lot of improvement is there in the build time by using this particular feature. Now, here is the scope to research this particular thing, because if you consider the manufacturing processes, most of the manufacturing processes like cutting is there, milling is there, even foundry as a manufacturing process have their own tolerances. If you want to cast a particular material, some tolerances are provided. If you want to cast a particular material for the pattern, also tolerances are provided. Even in machining, lot of tolerances are provided. But unfortunately, in 3D printing, the aspect of tolerance is not available yet. For example, if I want to print a PLA, if I want to print a particular metal, if I want to print a particular composite, how much tolerance should be provided to get the accurate geometry is not available. To overcome this, you can use option which is known as the horizontal compensation. By using this option, what we can do is you can slightly increase or slightly decrease the tolerance of your part. For example, let us say I want to produce a square whose size is a cube rather, whose size is 40 mm. But because of the heat used in the diffusing the material, most of the times it will be with the lower sizes than the 40 mm. So for that we need to increase the size. Now with the conventional slicing we cannot increase the size during the printing. But with horizontal compensation we can increase or we can decrease the size. For example, here I have shown two aspects. One is known as the positive horizontal compensation and one is known as the negative horizontal compensation. With positive horizontal compensation, what will happen is here actually the black line represents the actual component to be created or actual geometry to be created, and the green line indicates the tolerance which we get by using the compensation. So what will happen is if I provide the positive compensation to a particular part, it will increase the size of exterior part, means outside dimension will increase and inside dimension will decrease. For example, outside dimension is the these edges, they will increase, and inside dimension is this hole, this will decrease with positive compensation. If I reverse it with negative compensation, outside dimension will decrease and inside dimension will increase. Now, this is very interesting feature. We are also doing a lot of research in the horizontal compensation. In fact, we have published some essay papers on this on the horizontal composition. Lot of work is to be done in this particular aspect. If someone can develop an algorithm in which we can provide a rough or a tentative tolerance to be given to a particular polymer family, that will be a huge contribution to the society of 3D printing. So you can take this as a challenge to work on the horizontal composition. We are also working on it. The one of the last feature, because in this time I cannot explain almost all the slicing techniques, but some of the options are if suppose we are producing the hollow components like this model shown in the figure is there, some glass-like structures are there, some hollow bodies are there. We can use the base mode, which is available in most of the slicers. Now here what it will do is initially it will print two solid layers which is visible in the blue color, and after once the geometry starts, it will print the hollow components, which is not possible in the conventional slicing. And one of the last advanced slicing technique that I am going to describe is known as the adaptive slicing. This simply can be called as a variable layering. In case of conventional 3D printing slicer, what will happen is we actually print layer by layer. So that layer thickness is constant throughout the printing. For example, if suppose I keep the layer thickness at 0.2 mm, it will be 0.2 mm throughout the body. But in adaptive slicing, what will happen is it can give us an option for variable iteration. Means in the same object we can produce variable layers. For example, here this one is with the constant layer, right? I don't know whether it is visible clearly the layers or not. And this one is with the variable layer, right? If you do observe the part up to the half of this semicircle, it will be with the larger layers, and the rest part, which is the circular part, it is with the smaller layers. On the right side of this, it is visible, just in this. These layers are with the 0.4 layer thickness, all this, and from this, the layer thickness increases to 0.1. This is one more example. The same object is printed with static layers. This one is with the static layer. This one is with again with the thin static layer, and this one is with the adaptive layers. Adaptive layer means in the simple one body we can print the components with the multiple layers. So to sum up the traits in the slicing, we can go for advanced slicing techniques like adaptive layer thickness. We can have a support structure optimization, even integration with AI and machine learning tools. As I mentioned, for finding out the correct tolerances. Even cloud-based slicing tools are there. Multi-material slicing is one of the issues. So many aspects are there that you can do research with. So in slicing again, lot of opportunities are there. So with this, I end my small session of the material and the slicing. So we are doing a lot of research in the area of 3D printing, wherein in our lab almost all facilities are available. If anyone wants some help, you can approach to me. You can mail us. We can give you a solution. Thank you so much.
Sir, I have one query regarding this. Actually, do you have this metal additive manufacturing facility in your lab, sir?
We don't have one. We are purchasing it in the next month. Metal additive metal printer.
Oh,
Polymer we do have everything. Polymer we can print simple materials. We can print composites. We can print metal and polymer composites. We have printed almost 13 research scholars are doing research in our lab with the 3D printing research.
so which metal additive manufacturing are you going to planning for the purchase? For my information, this I ask.
Within 2-3 months, it will come to our college. We are with the specifications finalizing.
Okay, because powder bed usually they are another direct position. If you are planning, no, you can go for a direct position method. Because powder, this diffusion method, powder bed fusion, may not be economical because we need lot of powder for that. So just I want to give suggestion because we were struggling for that. Because we want to produce a component of suppose 50 gram or 100 gram, we need the powder requirement of 30 kg. That is the machine requirement. So in that case, this direct deposition method may be economical from the processing point of view. Okay, thank you.
Yes. Yes. Thank you so much. Thank you all the participants.
So we have planned this perspective that this session. Hello. Thank you so much, sir. The final notes complete the levy. We kindly invite Dr. R. Sir, Conference Coordinator, Assistant Professor, Department of Mechanical Engineering to express our profound appreciation.
Good morning, everyone. On behalf of Federal College of Engineering Technology, it is a great pleasure to propose a vote of thanks for the 6th International Conference on Recent Advances in Materials and Manufacturing 2024. I provide my sincere gratitude to our chief guest, Dr. Sunil Rayakar sir, Professor and Head of Mechanical Engineering, D.Y. Patel College of Engineering Technology, Kolhapur, who graced this conference with his thought-provoking address. Thank you, sir, for the inspiring speech. It is a pleasure to express my sincere thanks to our beloved secretary correspondent, to S.D. Chandrasekhar sir, and trustees, Mr. M. Yuvraj sir and Balasubramanian sir, who constantly supporting all these activities for this conference. Thank you, sir. I am tremendously thankful to our respected principal, Dr. M. Jayaraman sir, for his massive support and guidance for organizing this conference. Thank you, sir. And I like to mention my deepest sense of appreciation to the Executive Director of Energetic Solution, Mr. Kandaprakash sir, for anchoring us in the right path. Thank you, sir. And I wish to extend my sincere thanks to our organizing chair of Icramm, Dr. R. Kumaravan sir, for his untiring support in making this conference a successful one. Thank you, sir. And I would like to thank my faculty members of mechanical engineering, non-teaching staff members, and student volunteers who supported this conference. Thank you all. Last but not least, I wholeheartedly thank all the participants of Icramm 2024 for their sincere participation. Thank you everyone for being here today. Thank you very much.
Thank you so much, sir. As a tribute to the nation, I appeal everyone to join together in singing
तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाना जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 जन गण मन
Let us have a small break for refreshment for 10 minutes just outside the hall. What was the start your presentation here? So we divided this group into two. Hope you know the venues and presentation. Go to the respective hall. Paper ID 1089 2010 2028 2076 2077 2078 2079 2080 2081 2082 2019 and 2034. Authors are asked to wait here. We have a presentation in this venue itself. Other authors are asked to come to mechanical mechatronics lab. Professor D. Senthilkumar is there.
Yeah.